All right, good afternoon, everybody. Thank you for all the brave souls that came in today with the unpleasant road conditions. And I know there's quite a few folks online too. So great to have you all here for Ethan Gutmann's seminar. I'll do a brief introduction. There's a lot to say. I was looking through his resume and it's very impressive. He's a project scientist 3 and interim director of the hydrometeorological applications program here in RAL. And just going back through the history, he got his Bachelor's of Arts in Geology and Computer Science back in 1999, Williams College, which is in Massachusetts. And after that, he came here to Colorado to work on geology for both his master's and PhD, wrapping that up in 2008. And then, like many of our great people here, he came to work as an ASP postdoc, and we're lucky to have him here still today. He works in a large array of activities I was looking through, and I couldn't possibly hit them all, but these include orographic precipitation, climate change impacts, soil hydrology, snow science, convective precipitation, water resource impacts assessments, and built a lot of really interesting tools as well, including the intermediate complexity atmospheric research model. And then I had to include this one because I really like the acronym, Ensemble Generalized Analog Regression Downscaling Tool, which is OnGuard. And then it's done a lot of really interesting things too with observational techniques, like putting videos to detect tree sway, to understand drought conditions, and I'm sure I'm not doing that justice, but it seemed really interesting. A lot of cool stuff with lidar and other observation techniques. And also, on top of his 75 peer-reviewed papers and success with proposals, he served as a mentor, collaborator, supervisor to many in the lab, and also outside of the lab, including serving on PhD committees. So with that, I'm happy to let Ethan take over and present today on his work.
Thanks, Chris. And I will touch on a lot of these different topics Chris mentioned, and hopefully make this a bit of a fun just presentation of the journey I've been on for the last 20 some odd years. I'm going to start off going way back to that time in Williams College and hard rock geology, thinking about ancient rocks and where I started. So I'll give you a little bit of an overview of my education and early endeavors. Yeah, that is in fact me 25 plus years ago. And where I've really settled into this niche, thinking about water resource applications in particular. And then I'll spend a brief time, if I actually still have time, I've got a lot in here, going through some of the future innovations we're working on and applications yet to come. And sort of throughout this, I'll try to have some interesting interludes interjected along the lines of the videos of tree sway, for example. Many thanks before I start to a really, really long list of collaborators who have worked with me over the years. Many of you are in the room. Thank you very much. Some who aren't. Going back to my undergraduate advisor, Rona Cox, or Alex Getz, Eric Small, Martin Clark, Roy Rasmussen, Jessica Lundquist. Like I couldn't keep putting names on here. There's a ton of people I've worked with. I'm really indebted to all of their feedback and inspiration. So going back to the past, right? I really did start off looking at hard rock geology. There's another picture of me from 98-ish, standing on conglomerates in Arizona, where I was doing a very, I put academic in quotes, a very academic research looking at hard rock geology, quartz pebble conglomerates that were 1 billion years old, and trying to understand how they had evolved since they were deposited as rocks. And so we were going out collecting rock samples and slicing them into thin little slides we could put in a microscope and measure the contact between grains. If anybody wants to talk more about intersection of grain contacts and dissolution within sands, it's really kind of amazing, all the stuff that goes on in rocks after they're created. And as Chris mentioned, I was actually a computer science major as well, so I spent a lot of time working on Sun Microsystems workstations back in the good old days, many nights till 1 a.m. in the Sun lab at Williams. And that, well, I put that as a little bit of a footnote. that computer science degree has served me really well. I would say probably I used 90% of the work from computer science these days and only 10% of the hard rock geology work, even though that was my focus. And I did find that to be a little bit too esoteric. It just was not applied enough. And so in looking for graduate school, I moved out to CU to do something a little closer to actionable here. We were looking at sand dunes, which admittedly at this point we're talking about maybe tens of thousands of years old, so still not exactly modern day, but those sand dunes are still there. So this is a satellite image around Ruggin, Colorado. You see Ruggin down here. This is just a few hours east of here on the plains, and you see all these sand dunes that are impacting farmers. So they'll be in the middle of fields, they'll sort of enter the field, causing problems for agriculture. And so we were starting off looking at this with Landsat back 25 years ago. It was really hard to get Landsat scenes. They cost $700 per scene, and you had to have each scene on its own CD-ROM that you're loading in one at a time. So it took a tremendous amount of effort to do this. It's amazing what you can do with Google Earth Engine these days. Our computers were a little faster than they were at the time, than they were in undergrad, but still not terribly fast for handling this level of data. And we're also doing some fairly early, really highly distributed hydroecological modeling, where we were trying to model the carbon growth in plants in the rangeland using the Century model from CSU, so that we could then simulate how grasses in this area were responding to climatic factors and what we may be able to then tell people about how sand dunes would activate. And this starts to get a little bit more active, but what I realized here was that what I really cared about was the vegetation, and I didn't want to be a biologist. And that was all really controlled by water. And what I found more and more is that water controls everything. So moving into my PhD, I focused much more on water. I was looking at soil hydrology and trying to understand how we could better model water at the land surface. So you see at the top right here are plots of latent heat flux, essentially evapotranspiration from the NOAA land surface model over time in a semi-arid area where there's very little ET, and then a rainstorm occurs and there's a lot more ET and it decreases. Each of those black lines are model simulations with different observed soil hydraulic properties. So this is from a collection of 1,000 different soils. We ran through the model and said, these are actual measured soil properties. How much variability is there in the response? And you can see it's tremendous. Now, when we run the NOAA or NOAA-MP land surface models today, we use soil texture to say, well, we know what the soils are. We've mapped this everywhere. The bottom plot here is with one soil texture class. The top plot is with a different soil texture class. The degree of power that soil texture has in determining soil hydraulic properties is very small. It's on the order of an R-squared of 0.05. So we think we're specifying soils in our atmospheric models. We have no idea what soils are. And what we did at the time was use MODIS satellite data, thermal data, to say, okay, this is our default land surface model simulation compared to observed evapotranspiration. If we optimize the model, the soil hydraulic properties in the model, to better fit the MODIS skin temperature measurements, so we had no ET measurements, we just had skin temperature, you end up dramatically reducing the errors in the model. The bias is reduced by something like 90%, from 50 watts per meter squared to 3 watts per meter squared over a large collection of the DOE ARM sites in the central US. And you can see we had super fast computers at this point, right? And also as part of my PhD, I got to spend a lot of time in the field in the Sevieta long-term ecological research site, trying to measure soil moisture and evapotranspiration to better understand how, what's really happening in the real world, not just what's happening in our models. And not surprisingly found that measuring anything is really, really hard. So there's a phrase that I always love, which is that nobody believes a computer model except for the person who run the model. Everybody believes an observation except for the person who collected it, right? Until you've gone out and collected it, you don't know how hard it is. And so as sort of a first fun science segue here, I want to talk about a different measurement around this time, we started working with a geodesist at CU who was trying to look at GPS signals and plate tectonic motions. And she was finding all this noise in the data that had a very strong pattern to it. So what I'm showing at the top right here is a plot of the signal to noise ratio recorded at a GPS instrument over time. And there's some normalization that's happened here to remove some bulk signals. But time is really represented here by the sine of the elevation angle of the satellite, because what's happening is that as a GPS satellite is rising, the two paths, this direct path of the signal to the sensor and the indirect path where some of this signal is reflected off of the ground in front of the GPS and returned to it, these two paths change lengths at slightly different rates. And as a result, the two signals, the reflected signal and the direct signal, come in and out of phase with each other over time. And the frequency with which they're coming in and out of phase with each other is a direct function. You can work out some pretty simple geometry of the height of the antenna above the reflecting surface. Now, the cool thing is when it snows, all of a sudden the reflecting surface is now 35 centimeters higher. And you can do this, so the bottom right here is a simple model of what we would expect the signal to noise ratio to look like after snow in black and with bare soil in red. And you can see how well that corresponds to GPS observations after snow and with the bare soil. But here, this is challenging. We started off going out and measuring, looking at the climate reference network snow depth measurements made at Marshall Field Site. And you see that in these lines here. There are 3 different sensors. And then you see the red dots are all of the GPS snow depth measurements. And we kept looking at this saying, what are we doing wrong? What's wrong with the GPS data? It seems like it's biased high all the time. And so I went out and started measuring the actual snow on the ground and found that, gee, actually the GPS sensor was about right. The GPS sensor was making a measurement over a much larger area and of snow on the actual ground. Well, the really highly calibrated, beautiful snow depth sensors were making a measurement on a platform that was about 10 centimeters above the ground. And so as soon as you got your first wind event during the storm, it leveled out the surface of the snow, and all of a sudden the snow depth that was being measured by this system was about 5 to 10 centimeters lower than the actual snow depth in the surrounding area. We wanted to take this to, again, places where people care more about the snow. This is my journey into applications here. And we're trying to measure snow depth at Niwot Ridge, so up in the mountains, where this is in the water supply for Boulder, the city of Boulder. We installed a GPS sensor at Niwot Ridge, and then because it takes a day to hike up here and make a single measurement, we couldn't do that. So I built a terrestrial scanning lidar you can see in the background here. This is actually still sitting on the bookcase in my office, so if anybody wants to come see a 25-year-old terrestrial, actually at this point only 10-year-old terrestrial scanning lidar. We were able to use that to map out what you see over here, and let's see if I can get this to play again. To map snow depth, there's going to be a way to do this. Yeah, that'll do it. But I really want control over it. Damn it. Too complicated. Okay, well, what you might see, oh wait, maybe I have it now. No, I don't. What you might see is that at some point in here, there's actually a snow dune that goes moving across the landscape. So with the terrestrial scanning lidar, with these maps of snow surface, we're able to map out snow processes that I've never seen anybody able to map before. It's right coming in right here on the left side. You're going to see an orange dot there, just fly across. So super cool. You can see from the area around here that wind is really controlling snow in the mountains, and I'll come back to that again. So really cool, fun side project of sorts. And this really brought me to where I've been for the last 10 years, 15 years, focused on water resource applications, which I see as this finally helping humanity, right? Working with people at the Bureau of Reclamation, the Army Corps of Engineers, and other stakeholders to help them understand water resource impacts. And some of the major problems we've focused on are, how much water will they have this year? So making measurements and modeling mountain snowpack. How is climate change going to affect their basins? Particularly trying to downscale information from global climate models down to the basin scale of interest. And working also on flood impacts. How are different floods likely to occur, even just in the historical period? What have we missed in the future period? How are they likely to change? And so one example here is the Yakima River Basin. And I like this example because the Yakima River Basin has 6 major reservoirs run by the Bureau of Reclamation. So this is an area with a lot of water resource management activity. And importantly, if you look at the map on the top right here, the Yakima River Basin is on the east side, the downwind side of the Cascade Mountains. But when you're trying to think about climate projections, you're dealing with data coming out of climate models with topography that looks like these green blobs in the bottom. And the resolution in these models is so coarse that they can't resolve the Cascade Mountain range. As a result, they depict it as just a slow, gentle ramp from the ocean into Idaho. They're not representing precipitation generation mechanisms in the right way for this basin. And so we wanted to understand, how could you better simulate what's really going to happen to orographic precipitation in this area? And felt like a lot of the methods that were being used at the time, these statistical downscaling methods, were just taking precipitation out of the climate models, which we already said was probably generated the wrong way, and kind of rescaling it. And so we realized that WRF could do this really well. It's just out of the box, it was done. The problem was WRF was a little too expensive to run for tens of different climate models and hundreds of years of simulation each. And so I spent a lot of time early on building what is called the Intermediate Complexity Atmospheric Research Model, or NCAR, trying to take the information that we know and understand about the atmosphere and simplify it down a bit. So here we're using, analytical solutions for how air should flow over hills, mountains. You can see it. The airflow patterns here look very much like what you get out of WRF. Applying those analytical solutions within a high-resolution three-dimensional grid and taking the low-resolution three-dimensional data from the climate model. And now we can run a lot of the same physics that you run in a model like WRF, where we're advecting heat and moisture around in 3 dimensions, running the RRTMG radiation code, the BMJ convective scheme, the Thomson microphysics, the NOMP land surface model. But because of some of the simplifications we've made, we're able to reduce the number of model layers and take a longer time step and skip on the dynamics entirely almost, and run the model 100 times faster than WRF, which means now we can suddenly run these scales for the hundreds of years of climate projection that we need to include. And we do some idealized testing and say, look, if you run WRF in this perfect way, ideal experiments, ideal hill experiments compared to NCAR, you get virtually identical answers when it's exactly the right setup, right? In a broader variety of configurations, different environmental conditions. Again, very, very similar comparisons between NCAR and WRF, with sometimes where there's a little more differences. But more importantly, you can take this framework and apply it in real-world environments where we're now forcing it with era-interim reanalysis. What you're seeing on the right here is a simulation from NCAR. The blue is pulses of moisture coming off of the land surface every day. The green to orange colors are precipitation interacting with the high-resolution topography. And after running this simulation for a year, you can then compare the annual total precipitation in NCAR with the annual total precipitation in WRF, and see there's really a tremendous amount of similarities between these two. I won't say they're identical. There are some clear problems and deficiencies because of the simplifications we have to make in NCAR. But we're now getting something that actually looks like we expect this seasonal precipitation to look like, unlike what you get out of the global climate models. And importantly, when you look at the climate change projections from them too, here you're seeing climate change projections from 2 members of the CESM large ensemble at the top, as simulated by WRF in the middle, and then as simulated by NCAR at the bottom. And well, again, I won't say NCAR is exactly the same as WRF. It's putting the changes in precipitation in approximately the right locations now with similar magnitudes. Some additional bias correction needed before running hydrologic models, but we're getting the right physical processes represented to understand how orographic precipitation should change. Unfortunately, even NCAR has a fairly high computational cost to it. And so now we move on to the fun acronym, which is not on guard, but on guard. ChatGPT thought it was funny. So NCAR has a lot of costs, and we want to be able to look at even larger ensembles while still making use of the atmospheric circulation information from climate models and our physical understanding. So on guard is a statistical downscaling, shallow machine learning algorithm to downscale global climate models while incorporating atmospheric circulation patterns. We can put in any variables of interest. And I'll say the G in on guard is really important, that it's generalized, so it's fairly easy to flip a switch and change which algorithm it's using under the hood, change which variables it's looking at, and try to really understand why it's doing some of the things that it's doing. I've got a complicated flow chart if anybody really wants to look at it. I don't really want to look at it, but it's there if you want it. The G part I referred to allows us to now, for the first time, look within a common framework at what all of the different decisions we make in trying to generate actionable climate projections do. So what you're seeing in this matrix of simulations is the change in mean annual precipitation. In the different columns are different algorithms internally, and the different rows represent different collections of input variables that you give to those algorithms. And so you can very quickly see that when you're looking at mean annual precipitation, your choice of algorithm has very little impact on your climate change signal, while your choice of input variable, whether you'd use just precipitation at the top here, or try to make use of water vapor and winds, or try to throw in 10 different variables with surface pressure and winds and precipitation, you get very different climate change signals depending on which variables you tell it to even look at in the first place. And one of the really important things here is that there's a huge literature out there of how do you downscale climate models. It is almost entirely focused on what should your algorithm be. There's very little discussion of what input should we be giving it, when clearly that's the dominant effect in most of these cases. And I'll say part of the reason there's this focus on what algorithm should we use is because that's one you can actually verify in current climate, right? So when you're seeing different climate projections, it's really hard to verify which one of these is correct. However, if you look up here, I'm showing the probability distribution function of precipitation coming out of GARD with different algorithms and different input variables. If we just zoom in on the top there, now all of the solid lines use one algorithm. The different colors are different input variables. And here you can see actually the algorithm selection choices do matter. This is where you don't get enough extreme events if you're using a simpler regression style approach. Even if you're using a more sophisticated analog approach, but you're not including a parametric fit at the end. And then when you do a more holistic approach where it's sort of akin to a regression tree, so these shallow machine learning algorithms, you get a better fit to the observed black line of the probability distribution function. And indeed, when you look at the climate change signal for extreme precipitation now at the bottom, there's still more of an impact due to variable selection, but there starts to be a fairly large impact due to your choice of algorithm as well. So starting to elucidate some of the things that control our future projections, not just how well does it simulate current climate, has been a core feature of GARD, or UnGARD. But as we mentioned, what we want to know is which of those future projections is correct, right? That's what everybody asks is, okay, which one should I use? But we can't go 100 years into the future, figure out which one's correct, and then come back and use that one. So what we're doing instead is trying to split up the historical period into different climate modes. So we can use ENSO as a proxy for this and say, well, if we look at the precipitation in different downscaled data sets in a positive ENSO state versus a negative ENSO state, and now we can make maps of the correlation between ENSO and precipitation directly from the climate model on the top left here, and from 5 different statistical downscaling methods, and the panels below there, and start to see fairly different patterns pop out. In particular, you see northern Colorado actually probably flips the sign a little bit here, and you don't see that at all in many of the statistical downscaling algorithms. Similarly, the Yakima River Basin, right, downwind of the Cascade Mountains, probably has a little bit of a flip, or at least less of an influence of the ENSO, whereas a lot of statistical downscaling algorithms are just taking what the climate model had. Now we can take this and look at what the observations tell us and try to say which one of these is correct. And unfortunately, it's not a perfectly straightforward answer. There's still a lot of ambiguity here. But very quickly, you see that in the observations, there is a little bit of a flip in sign in the northern Colorado Rockies. There's a little bit of a flip in sign downwind of the Cascade Crest. And so that starts to give us a little more confidence in some of these downscaling methods that are making use of atmospheric circulation features. But when you actually run some of the statistics, it's harder to say which of these is best. The RMS error on this might be better than the RMS error here, even though this is clearly giving us a spatial pattern that's more interesting and shows it's representing some of these processes. And we can do this with WRF as well. There's some details here to go into, so I'm going to skip over this for now. Finally, we can take these algorithms and start understanding for a specific application when we look at, say, the Colorado River Basin, where there's a tremendous amount of interest on the impact of climate change on water resources. And we look at the average climate change signal across multiple downscaling methods, and this is averaged across climate models for each of multiple downscaling methods. You see that the statistical downscaling methods at the top here all have fairly similar answers, while the more dynamical methods such as NCAR or WRF is a little complicated because it's actually a PGW future. There are differences here I'd be happy to go into. But both of these project a somewhat different future climate projection than the statistical methods that are a little bit more sort of washed out. And we take this and say, okay, well, we have a little bit more confidence in the dynamical methods, but NCAR, we're not so sure about the convective processes. GARD isn't giving us everything. What does this really mean for the hydrology anyway? Because all of these are kind of the same washed out greenish color. Now, if you look over the entire Colorado River Basin, now I'm showing you two downscaling methods, LOCA, which is used in the National Climate Assessment and has been widely used by water managers, and NCAR, which is a fairly different dynamical method we've talked about here. What you see is they both have a similar representation in the historical period compared to the observations observed streamflow at Lee's Ferry in black. So Lee's Ferry, for those who don't know it, is down at the outlet of the upper Colorado River Basin. This is where Glen Canyon Dam is. Lee's Ferry is just below Glen Canyon Dam, but it's basically at Glen Canyon Dam. And you look at the climate change projected by LOCA and NCAR, and while there's a difference between these two, it's not clear that that's even statistically significant, the difference, when you look at the variability across all of the different global climate models. And so this starts to say, like, well, maybe for this scale basin, climate downscaling method doesn't matter that much if you're just looking at these large scale properties. However, when you start drilling down into smaller and smaller watersheds, where downscaling might matter, you start to see much larger impacts and clearly statistically significant differences, even given the large spread in global climate models. So if you're Denver Water and you care about the Blue River Basin, you might really want to think more about how you're evaluating climate change, because it's a fairly small basin nestled in the mountains. So I'm going to step back now and switch gears to the other aspect of water resource applications, where I've been focused more on mountain snowpack and how we can both measure it and predict it in the current climate, as well as thinking about future climate impacts on mountain snowpack and just the hydrology. And within this, I want to point out in this image that there's a tremendous amount of variability in the snowpack at high elevations due to those wind redistribution processes I mentioned earlier, where snow is always accumulating in these deep snow drifts at the top of mountain ridges and getting scoured off of exposed areas. And then in addition, we have forests over all the rest of the area. Even within the forest, there's a fair amount of variability in the snowpack, but the forest itself has a lot of complex processes that we don't know how to measure. So this kind of brings us to fun science fact number 2, thinking about images of tree sway. So I'm showing you here is a video of tree sway at Niwot Ridge. This is captured from the Ameriflux Tower looking down. You can see all the trees swaying in the background. And you'll see these like puffs of snow. You'll see one come off in here in a little bit. Because even though you don't see any snow in the canopy here, there is still a fair amount tucked in between all the needles. But it's something we have almost no way of measuring. And so we've spent a fair bit of time trying to find better ways to measure this. And it turns out that these videos themselves can tell us. So there's some fairly basic engineering physical principles that tell you that the frequency with which a beam sways back and forth, its intrinsic frequency, is driven by its length, its mass distribution, its modulus of elasticity, all properties that stay pretty fixed on a tree until you put snow in the canopy. So we can measure from this video how fast, or the frequency really, not how fast, the frequency trees are moving back and forth, and start to distinguish between time periods where there's a lot of snow in the canopy and less snow in the canopy. A former postdoc here, Mark Raleigh, now at OSU, did a paper recently looking at accelerometers in trees to measure sway frequency and showed that that was related to canopy interception. Here you're seeing an image of the frequency that each individual tree is swaying at. This is done just using a Fourier transform on the brightness of each pixel within the image. So we're doing like pixel by pixel frequency calculations, which also means you can look at bushes and you can start to look at individual branches within a bush and look at how that's changing. Now, it turns out there's more work to do to get the resolution of the frequency measurement accurate enough. But first order principle, it's pretty cool and has a lot of promising applications, both in understanding physical processes and snow interception, rain and snow interception, as well as looking at drought response. So this area in New Mexico, they'd actually killed off half of the trees, and we're trying to understand how rapidly that affected different bushes. So we were trying to put out a few canopies there, a few cameras there, because the drought stress response changes the modulus of elasticity of the tree. When it first starts to lose water, it's losing water pressure within the cells, and so the stem actually becomes sort of floppy, and you change the frequency, and then when you start drying it out, you actually get more rigid and you get a much higher frequency. So there's been some other papers working with a group at the University of Wisconsin looking at tree sway and drought response. So lots of cool things here, right? This is just fun. And you might say, oh, this is great, but if you have to put your camera on top of a tower, the tower is so damned expensive. Well, who cares if you're saving a little money on the camera? You can also just take a camera and put it on the ground looking straight up and do the same thing. So I don't know if this is art or science, but this is just me putting my iPhone down in a forest, filming straight up, and then doing this video processing. You can see the, where's my laser pointer? You can see the tree stem sticking up here, and then you can see how the crown of each tree has its own intrinsic frequency. Figuring out how to deal with the noise, in a sense, in here has been a problem. We don't quite know how to separate out when you've got a range of different frequencies in here, because it's probably not the average. It might be the mode. It might be you have to look at combining frequencies in different ways. Joe Amatelli, a grad student at University of Washington, has really been digging into the details here and has a paper just about to come out. I should say just about to be submitted. So finally, talking about not canopy interception now, but another snow process that's been really important for water resources, which is snow redistribution in the mountains. So as I mentioned, one of the dominant features is often the variability of snowpack in any sort of complex terrain when there's wind involved. Even behind individual tree clumps, you get these downwind patches of snow. When you fly across, so when you flew to New Orleans for AMS, if you looked out the window, at least on the way back after there'd been fresh snow, you see the variability in snowpack even just across agricultural fields. So snow redistribution is kind of just the norm when you have snow on the ground and wind, but it's not in most of our models, and it turns out to have fairly large impacts on the timing of melt and therefore water availability, as well as when you think about climate change impacts, that's going to change the redistribution of snow, it's going to change the melt rates, and the snowpack spatial variability feeds in there. There's also some feedbacks to the atmosphere in terms of the albedo of the landscape. As I mentioned, this snow redistribution really isn't in a lot of our computer models right now. So if you were to run NOAA-MP over a region of complex terrain in the mountains, you would see more snow on top of the mountains and less snow in the valley bottoms. However, Glenn Liston at CSU built a model called Snow Model a while back to explicitly simulate the redistribution of snow from the upwind side of a ridge to the downwind side. So you get these drifts. Unfortunately, Andy Newman tried running this, it was probably 10 years ago or so, and we were so hung up with the computational cost of it that it was hard to make a lot of progress. You could do it, you could look at things in ideal case studies, but running it over, say, the whole world or CONUS was challenging. So we had a project with NASA where we were parallelizing snow model. You imagine since there's now advection involved, it becomes a much harder problem to parallelize. But we were working with NASA so we could better plan out future satellite missions and make use of future satellite missions to build a global snow product. And in the meantime, we parallelized snow model. This is an image from Ross Muller's work showing snow model run over CONUS on a 100-meter grid, explicitly simulating the snow drift formation in the Indian Peaks. You see every little drift of snow captured, albeit every little drift of snow that you can measure on a 100-meter scale. Right? There's smaller drifts within that. And now we're able to simulate explicitly some of the processes that matter for water management. And we're working with them right now to better compare this with, say, the variability we see in airborne lidar surveys to help plan out where to put future instrumentations, working with NRCS and US Bureau of Reclamation. And we can use this to run some simple sensitivity experiments where we take a small ideal domain and add different temperature perturbations and see what that does. And it turns out that increasing the temperature reduces the amount of snow redistribution you get because you now have sticky snow and a little bit shorter snow season, which decreases the coefficient of variability of snow around peak SWE until you start to remove all the snow, and then the coefficient of variability explodes, right? But generally, reducing the variability is going to change the melt rate of snow maybe more than the warming itself does. And this is obviously driven by a lot of complex atmospheric dynamics, so I'd encourage anybody in the room who's interested in complex flow over terrain. Here's a simple lattice, 2D lattice-Boltzmann model I built a while back just so I could simulate an immersed boundary condition and look at airflow. And indeed, you see this flow separation downwind of mountain ridges that corresponds perfectly with where you get snow drifts downwind of mountain ridges. And we can see this flow separation in terrestrial, Doppler lidar scans. So what you're seeing here, these couplets of orange and blue are where you have large recirculation features. So you see this really large eddy coming off the top of Gothic Mountain here, scaling down to smaller eddies and sort of disappearing in turbulence at the bottom here. So trying to think about how can we better parameterize some of these very nonlinear atmospheric dynamics. Which leads us a little bit into fun science number 3. Larger scale measurements provide more information. And I'll come back to the fun part, don't worry. So this is looking at, I mentioned before, the Airborne Snow Observatory, ASO, LIDAR surveys of snow depth. Here you're seeing the Tuolumne River Basin in California, and the color is essentially how correlated each individual pixel is with the basin mean snow water equivalent. And so you can see this is essentially trying to look at the question of if the NRCS or other groups were to install a new snow observation, which points on the ground have the most value in predicting the basin mean snow. And what we find is that with the 3-meter snow depth product, the correlation coefficients are fairly high, but interestingly, if you just average that in spatial scale up to 50 meters, you get much higher correlation coefficients. So clearly, making measurements over larger areas and or tamping down noise by averaging over larger areas pretty significantly improves your ability to represent water resource management applications in these kind of snow-dominated watersheds. But you might also say, well, we already have a whole bunch of SNOTEL sites out there. We have lots of measurements. We want to add a new measurement. Where should we put that? Because those are already measuring a lot of this variability. It turns out if you remove the variability that we already know about from SNOTEL sites and try to run the same analysis again, what you're left with is, gee, the locations you need to measure, these red areas, are at really high elevations in the mountains where snow redistribution plays a larger function. So this is something that we're not measuring with our current measurement network right now. So now I've told you we need large scale measurements and we need measurements above tree line, high alpine areas. Those are both really hard problems. We don't have a lot of measurements. Except if you recall back to fun science factoid number 1, we do have the GPS system and more importantly, terrestrial scanning lidars, which are a little easier to put out in a variety of complex environments. At the time, the lidar I built 15 years ago was measuring a 1 point on the ground every 10 seconds almost, and then I had to program the data logger to move to another point. Anybody who's had to program a CR1000 to do loops over, it's a pain in the neck. Now, self-driving cars want lidars too, and so we're able to get a lidar for about 1/10 the cost that measures not 1 point every 10 seconds, but 100,000 points per second, and makes measurements. What I did here is take out a Livox mid-70 lidar system in the East River Basin as part of the Sublimation of Snow SOS field campaign. And we were able to map snow. What I'm going to show you in this animation is the change in snow depth over time after a snowstorm, every 5 minutes now instead of every hour. For reference, the X and Y axes here are meters of distance. Some of these artifacts are because there are guy wires from towers that are located in the center here. But if you watch this, you remember the very blurry first instance of snow dunes that we had 15 years ago? Now you can see snow dunes in all their glory. And you can see them changing directions as the wind shifts. You can see when somebody skied into the towers to monitor. So this is one of the EOL technicians working with us here. And you see this even after it's mostly gone. You still see these patterns moving across the landscape. There's snow dunes everywhere. And then within this, you see all these sharp features. So there's a lot of spatial variability in the snowpack generated by wind redistribution. So we finally have some cool ways to make large-scale measurements of snow for water resources in areas that are very challenging to instrument. So there's a lot of work coming up now, particularly with the Bureau of Reclamation and Army Corps to look at better understanding uncertainty in future climate projections. A lot of work with various groups to improve NCAR wind fields so that we can better simulate some of the nonlinear dynamics. And then working with CISL to jump all the way to a pure machine learning-based application of atmospheric models or instance of atmospheric models. Also continuing to work with NASA and the snow community to develop new snow missions. And then trying to improve, this is a kind of cool final fun science piece I'll jump into here. Better understand ET in complex environments. And to do so, we're trying to measure water vapor in 3 dimensions now. So lots of cool ways to look at uncertainty in extreme precipitation for reclamation using NCAR. Working with CISL to use their, let me see, get this to play, their machine learning code that they're applying to global problems, to regional convection permitting problems. And finally, the sort of final fun science piece, working with Rice University, who's developed this really cool way of creating a hyperspectral imaging sensor where they 3D print these fiber arrays to move every individual pixel in an image, spread them out, and then after you spread them out, you separate individual pixels, you run them over a diffraction grating or a prism to disperse the wavelengths. So now you've separated out the individual pixels, you can spread out the wavelengths from each pixel onto different image sensors. And now in real time, you can record video frame rates with something like 20 to 50 different spectral channels. And as a result, you can record those different spectral channels through water vapor absorption features to record on every individual pixel the total amount of water vapor from the plane to the surface and really back up to the sun times the reflection of it, right? It's complicated. But as the plane is flying over, it keeps measuring every point on the ground from 100 different angles because it has 100 pixels in the image. And now by taking all of those angles, we're working with a group at HAO to try to take this data and run it through their tomography algorithms that they developed for solar physics to reconstruct the three-dimensional water vapor field. So the water vapor field you're seeing in the background is an image that Jeremy Sauer gave me years ago from Fast Eddy. So doing some simple experiments and have a proposal in with NASA right now to try to actually build this thing and fly it. So lots of work. I hope there's been something of interest for everybody in the room today. Lots of cool side tangents and new observing systems. I think that's one of the things we really have to keep in mind, that fundamental new science often really needs fundamental new observations. You learn so much, and you learn so much as a modeler by going out in the field and seeing what things really look like. I encourage everybody to try to get a chance to do that. Working with various stakeholders, reclamation, the Army Corps primarily, very much indebted to funding from the Bureau of Reclamation, Army Corps of Engineers, NSF, NASA, NOAA, DOD, right, a wide variety of groups, including some international funding early on from Statkraft and Det Norsk Veritas. And throughout all of this, as I forget if you mentioned or I mentioned it, really working with a large number of students and postdocs. You might have noted in the last 5-10 slides, there were very few Gutmann et al. References. That's because more and more I'm trying to help the next generation learn how to do these things, and they can write the papers. So it's really been a tremendous journey from hard rocks kicking around in Arizona, breaking open rocks, literally, to today with supercomputing, scale simulations, new satellite instrumentation, lots of cool stuff. It's been a long, strange trip. So thank you all, and I'm happy to take any questions.
All right, fascinating talk. Thank you very much. We will take questions both in the room and online.
It's a microphone.
Yeah.
So thanks for the talk, nice talk. So I was curious if you can give me your opinion about, so you have shown many downscaling techniques. And so I was wondering if you have an idea how much is, you can kind of compare the uncertainty coming from the downscaling with respect to the uncertainty of different scenario. How much is the uncertainty coming from the downscaling technique important compared to the uncertainty that you can have with the different global ensemble members?
So that is
for precipitation, for example.
That is a fantastic question, and the answer, of course, is it depends. Sam Hartke in the back here has a cool paper coming out looking at this a little bit. The On Guard paper that I referenced, the Gutmann et al. 2022, I have a figure explicitly saying, here is where the variability is larger in downscaling methods, in input variable choices, and in climate models. And in some regions of the world, the climate model dominates, no matter what you do to the downscaling method. In other regions, how you portray some of the statistics in your algorithm matter. In most of the area, which variables you provide as input matter the most. Looking at the view of the Colorado River Basin, right? If you average over larger scales, maybe it doesn't matter at all. You really need to know the variability in climate models and climate projections. But if you care about the Blue River Basin or the Yakima River Basin, you really need to think about how you're downscaling. So as I said, the answer is it depends.
Depends on that.
Yeah, on the application, on the location, on the scale, exactly. And are you looking at mean annual precipitation? Are you looking at extreme precipitation? Are you looking at heat waves, right? And then within that, if you're using a statistical downscaling method, what observational data set did you use to train it? That ends up having a big impact, right? There's so many choices, and so just trying to document it so that end users are actually aware of what they're doing and what they need to think about more has been a core aspect of this, so thank you.
So on the last topic of evapotranspiration, you mentioned aircraft for the measurements. Can you also use a series of low-cost drones to get much more? Okay.
So part of the problem is that right now this imaging sensor is a little heavy to fly on a drone. You could, and there's actually some work. If we get this work funded, we're trying to miniaturize it further because we have an initial prototype that you can kind of carry as a suitcase, right? It fits on this table, so no problem to fly on an aircraft. We're also hoping to be able to put it, 10 years down the road on satellites because the power requirements are minimal. And there's no difference, right? All the water vapor is near the surface. And so whether you're flying an aircraft here or a satellite here, all of the signal in your water vapor absorption is coming from the area below you anyway. And be a cheap enough instrument that you can potentially put up a constellation of satellites in a train, overlapping, or at different angles. So you might have them running in parallel down, looking at different angles. There are lots of potential uses. I've talked about water vapor here. There's no reason you couldn't do this with other gases, right? Anything that has a significant absorption feature, we can tune this instrument to look at any collection of wavelengths. And you can trade off, do you want 100 channels and maybe you only get 50 by 50 pixels, or do you want 100 by 100 pixels and maybe you only get 25 different wavelengths? Lots of cool trade-offs that can be made with this technology.
Cool. We do have a question online by Thomas Martin. The continental scale groundwater folks are using machine learning emulation of these physical models to cut down on the cost of the computations and the cycles. What is the current breakdown of supporting current CPU models versus new machine learning GPU-based methods?
Yeah, so that's part of the reason to shift to these machine learning-based global models. I don't know the number off the top of my head. It is many, many orders of magnitude reduction in computational cost and energy requirements. The training is super expensive, how you train these machine learning models. But once you have them, running them, I think you're talking on the order of 10,000 times faster. If you just port a physical model to GPUs, and you do a really good job with that, you might get 100x faster. So part of it is you're able to leverage GPUs, but part of it is taking machine learning models here. You're able to implement equations that are deliberately fast on GPUs and other hardware, right? So one of the beauties of moving to a machine learning-based model algorithm is that you train it all up and you've just written it in this very high-level language. Running it on a GPU is trivial. Running it on the tensor processing units from Google is trivial. Running it on the wafer scale engine from Cerebus is trivial, right? You think about how much time we've spent, and we still haven't managed to port our physical models to GPUs, really. Like we sort of have, but not really. And how easy it is to move these machine learning models between new architectures. It's pretty amazing the power you can get. A little bit of a side tangent. I hope that answered your question.
Sue. Sorry.
Okay, so fun science fact number 3 had to do with larger scale measurements, providing more information, and you showed those nice plots where averaging, did give more information for that river basin, but obviously if you take that too far, you're back to the 1 degree climate models, which are way undersampled. So it seems like there's some sort of optimization there, and where would that be?
No, that's a great question. And it depends a lot. So part of the beauty of working with end users is that we have calls every other week with the group that runs the San Joaquin River Basin, And they're saying, yeah, okay, basin mean snow is great, but we also really want to know if you divide it into different elevation bands, what does that tell us? Is there a way to subset out different regions of the watershed? So most of their applications are at least at the sort of watershed scale, but they want to know variability within that. Here we're talking about going from 3 meters to 50 meters, so you're still vastly finer resolution than anything where that becomes a limiting factor. But ultimately, you need to resolve what matters to the end users, and that's typically something smaller than the unit that they're interested in. So if they're interested in the watershed, you need to have subgrid heterogeneity within that, but you don't necessarily need to go finer than that. There's some utility even to, there's some cool GPS displacement work that Tom Mensminger, who's not here, has done, looking at how a GPS sensor, how the whole crust sinks under the weight of the snow in, say, the Sierra Nevada mountains. And so there, with a single GPS sensor at a single point, you're making a measurement of snowpack over the entire mountain range. And they have struggled to say, like, how do you bring this back to end users? Because it's such a large scale measurement. In some ways, it's great that it's that large scale, but it doesn't tell you my watershed has this. So there's absolutely a trade-off in there. And some of that has to be done on an application by application basis. Like what's the optimal resolution for your case? I think for most, at least water resource applications, the answer is smaller than the watershed of interest.
Mm-hmm. Okay, we do have a question online from Sarah Tessendorf, who commends you on a great talk, and ask what resolution of snow depth does the scanning LiDAR from SOS detect?
I'm just going to run this again because it's fun. Oh, come on. There we go. So it measures individual points. What you might notice is that down here, it's a little noisier than it is up at the top of this. In this case, I have gridded it to about a 10 centimeter by 10 centimeter grid. At the far end of the LiDAR's range, the points, you're only getting a few points per box, and so when you average that, you're getting a lot of noise. Right up close to where the LiDAR is, so the LiDAR is actually off screen up here. Here, I'm pretty sure I could get down to 1 centimeter by 1 centimeter. The point cloud is just so much denser when you're close to the LiDAR. So there are a whole bunch of trade-offs in terms of how high up is the LiDAR, what area are you looking at, how long do you want to average over. So down here, you're getting a different point every scan, and so if you just average 10 scans together, maybe you can get down to the centimeter scale at further ranges. You do start to run into more noise just because when the tower itself flexes in the wind, it bounces around and it adds noise, and so there's some limiting factor at larger distances.
All right, I'm sorry, we're running out of time, so we're down to one last question. Rajesh first says great talk, and ask, are there any of the downscale climate projection data sets and subsequent hydrological model output that are used by decision makers? And if yes, how do the uncertainties in the final products affect the decision-making process?
Yeah, no, great question. And the answer is, it depends a little bit on how you define it. So we have done a lot of work. The slides I was showing here were presented at the Colorado River Basin Symposium. So this was really, it was not researchers. It was a whole collection of water users. We've transferred the data sets that we created to the Bureau of Reclamation. They're looking at it in their planning. We've transferred it to, it's available to Southern Nevada Water Authority, Denver Water, a whole collection of end users. A lot of our other work in the Pacific Northwest has been with the Army Corps of Engineers, and we've sent them all of the data that we've used. In the Pacific Northwest, they're trying to evaluate flood risk, and so they're looking at the variability in flooding from different downscaled projections and what that means. They're running that through their reservoir operations models locally to understand how the whole system would behave in these different settings. The Bureau of Reclamation for sort of large-scale water management, you notice, as I mentioned before, right on the basin mean, there isn't all that much difference, and so they're sort of looking at a lot of their existing approaches as well as ours to try to understand how basin mean hydrology is going to change. They have a decision-making framework called DMDU, Decision-Making Under Deep Uncertainty, where they try to understand how do you optimize decisions given just a huge amount of uncertainty. That is a research problem unto itself that we haven't tackled all that much ourselves, but I think it would be something that we need to learn more about and think about other places we can add more information to that decision-making process.
Okay, so we're unfortunately out of time for additional questions, but I do welcome you to get in touch with Ethan after this talk or in person in the building. And just want to say thanks again for the outstanding talk. Let's give him a round of applause.
Please come talk to me about rocks sometime. It'd just be a nice break.